What happened? Oh, okay. Thanks. I can take that. Yes. Okay. Okay. So, today I have um, uh, a staff from CC helping me in doing admission control. Otherwise, yesterday it was crazy. I was giving the talk as well as I had to do admission control because people kept joining at various times. But today I think is slightly better than yesterday. So let's see what happens. Right. So I'll start the thing now in a minute. Okay. So. Okay. Because everything is new, it takes me some time to get used to it. I'm also recording the lecture, so in case required, I can make it available on the web, at the end of the day. Okay. So yesterday we reviewed probability. Okay. Basics stuff. What is probability? What is conditional probability? And what is the prior and posterior probability, the Bayes formula, right, and the total law of probability, and so on. So I'm going quite fast because I don't want to elaborate too much on what is already known to everybody. I did a quick survey in the class last week, and almost everyone in the class either was doing the probability course now or had done it last semester or had taken a course from mathematics. So I think in that sense, it is not very different, right? It's a continuation of the same thing, right? So let me give some instructions. If you want to ask questions, please go ahead and unmute and ask the question, because I'm not going to switch screen. In Google Hangout, if I have to see who is asking questions, then I have to switch screen, and it takes away the momentum. Okay, so I will stay on my writing pad screen and not on the Google control screen. So I really don't come to know anything about who is joining and who's asking a question, who's typing a question, and so on. So if you have a question, just unmute and go ahead. Is that okay? Somebody? Can someone unmute and speak?
Okay, sir.
Okay, great. Okay, so I mean, just to know that I am talking to people and not to a blank screen. Okay, otherwise it's a very difficult process. I mean, I'm so used to looking at people's faces when I teach. Here I don't have a single face to look at, so it becomes very difficult whether I'm making sense, not making sense. People find it useful, not useful, right? Everything is a problem. So we talked about probability yesterday, and today I'll continue and talk about what is called a random variable, right? Okay. So yesterday we showed, we defined a few fundamental ideas in probability. We said we have an experiment. An experiment is something whose outcome is not deterministic, meaning I cannot say the value, what it will be at the outcome, right? And so outcome may be one of several possibilities, which we call as a sample space. So this is my sample space represented by omega, and it has several outcomes, and here I'm showing one outcome as omega, right? Capital Omega is the entire space, and omega represents one outcome, right? And to this we took several outcomes and defined that as an event, then we did several operations on the event, such as union of the sets of events or intersection of events, and based on that we define certain probabilities. And so today what we're going to do is, from the sample space, right, each sample in the sample space maps to a real line. So this is a real line, right? Takes values from minus to plus infinity potentially, and x is the mapping function, right? Some function. We'll see what it is quickly, right? So from the sample space of from individual samples omega, I use some function called x, and so this function of mapping, this I'm going to call that as a random variable, right? And so I'm going to use capital X to represent variable, or any capital letters represents variable, right? And the mapping is onto a real line, so it'll take some real value. Okay, then what does it mean? So the simplest idea is that of a Bernoulli random variable. Okay. Here, I get two values. X can take only two values. X is either 0 or X is either 1, right? So even though in the previous definition I said it can take any values on the real line, here I'm now pointing to a situation where X takes just one of two values, 0 or 1, right? So a certain X omega 1 takes me to 0 or is mapped to 0, and certain X omega 2 maps to 1. That's it, right? So the entire sample space, right? The entire sample space is now partitioned into omega 1 and omega 2, and this omega 1 maps to 0, this omega 2 maps to 1. That's it. So the entire space maps to this, right? So let's imagine that I can assign a certain probability p with this and 1 minus p with this. So probability that x takes value 1 is p, and probability that x takes value 0 is 1 minus p, right? And so I have a very simple definition here, because I have only two values to which the entire sample space maps, 0 or 1, right? And the probability that it takes the sample omega 2 is p, and other one is 1 minus p. That becomes the probability that x takes value 1 or x takes value 0, right? And so this can be extended to a situation where my x omega maps to is such that it takes value x1, x2, x3, and so on up to xn, where n can be finite, or n can be countably infinite, right? So then I can assign, right, probability that x takes value xi, because here x is taking all these values. X let's say is some pi, okay, because I have the entire sample space. The entire sample space is partitioned into n partitions. N potentially can be infinity, and each partition has a certain probability. And because we said yesterday, if you look at the entire space in the sample space, the total probability should add to 1, right? I whatever, going from 1 to n, or in infinity, right? The total probability adds to this. So this pi can also be shown, right, as a so I have the real number line x, and somewhere here is x1, somewhere here is x2, and so on. Somewhere here is xn, and with this I can indicate the probability. So this is p1. I can show that this by an arrow, and this as p2, and so on. and this as Pn, right? And by this logic, you know, if you add up all these values P1 and so on, it'll add to 1. And this way of representation is what is called the probability mass function. PMF for short. I mean, it simply means that, you know, with probability P1, X takes value X1. With probability P2, X takes value X2, and so on. So this is some kind of a distribution, right? So how the probability is distributed along these values. And as I said before, n can be infinity, right? And so imagine I have a sequence which takes probability that X takes value equal to n is half to the power of n, and n is 1, 2, and up to infinity. Right? Okay. Does that make sense? So in this case, if we add up, what is it? It's 1 by 1 minus half. That's equal to 2, no? So I should divide this by half then, right? Okay. Yeah. So it's possible that I have an infinitely long mass function where n takes values from 1 to 1 onwards. So X takes value 1, X takes value 2, X takes value 3, and so on. This is half into half. This is half into 1/4, and so on. Okay, and so it's an exponentially decreasing sequence, and if I add up all these values, that becomes equal to 1. Okay, so that's another variation, right? But this doesn't exhaust all the possibilities. The interesting problems happen when I have a continuous random variable. So now the events are a continuum, and you know, I'm mapping this by a function x to the real line. In this case, many interesting things happen. So as opposed to probability mass function, I now define you know, what is called the probability density function. It is represented as a small p of x. X is a random variable or the mapping function, and x, this is shown as you know, probability that the random variable x lies between x, we can even put the equality sign, x plus delta x, and you know, the infinitesimal is in the denominator also. So this is the definition of, let me make this into a lowercase probability, lowercase. Okay, so lowercase p. So here p is lowercase and here p is uppercase. This represents probability that the random variable is between x and x plus delta x, right? And so because it's continuum now, you cannot ask the question, what is the probability that random variable x takes value equal to x, right? That will always be 0. You always have to say now, you know, what is the probability that it is in a certain range of values? It takes, you know, a certain length on this. So only a non-zero length is meaningful because this is now a continuous random variable. And if the length is a point, then that becomes meaningless, right? So this is now what is called the probability density function. Okay. This allows you to ask the question, what is the probability that random variable x lies between some range a and b, assuming b is greater than a, right? Somewhere here is B, somewhere here is A. So I can now ask the question, what is the probability that X lies in this, right? And given this density function, you simply integrate the density function, right? Px by x dx between A and B. That gives the probability, right? So in that sense, this is a density. That is, when integrated, right, gives you the actual probability. So this is the probability density function, and often we keep calling this as PDF. Right? Instead of expanding the whole thing, we will call this as PDF. Okay, so very interesting. There are a number of interesting distributions possible. The first example I will take is that of a Gaussian random variable. Where the probability density function is defined as a 2 pi sigma square under root e raised to minus x minus m square by 2 sigma square, right? This Gaussian random variable has it's also called the normal distribution, and I'm going to use this notation script n to represent that. And a Gaussian random variable has two parameters. One is the mean, the m that appears here, that's appearing here, and the second is a sigma square, what is called the variance. We'll come back to the actual definition of variance, and that appears here as well as here, right? So interesting thing is here x is allowed to take value, right, between minus to plus infinity, right? So this is the entire x-axis. Okay, and if you sketch this, if this is origin and somewhere here is m, I'm taking m to be positive, need not necessarily need not be positive. So I get this symmetric bell-shaped curve, right, which is symmetric about m. That is, whatever you see on this side is identical to this side. Correct? It partitions the entire space into two regions, one less than m and one greater than m, right? And it is totally symmetric. And this equation, e raised to minus x minus m whole square by 2 sigma square, defines a bell-shaped curve, right? There are other bell-shaped curves which we'll also talk about when we come to it, but this is the most interesting bell-shaped curve, where the at some width of this, the width of the bell, right, or the shape of the bell is a function of a sigma square, right? If sigma square is large, it is flatter. Sigma square is small, it is narrower, right? Or it's peaky, right? So sigma square, so to speak, controls the shape of the bell, right? Very small sigma square, the bell is tall. Very high value of sigma square, the bell is a very broad bell. Okay. So in this case, you can ask the question, what is the probability that x takes value less than some real value x, right? And by our definition, it is minus infinity to x. Oh, I said x already. Huh? Okay, let me change it to y, right? And so y is just a dummy variable, right? Capital X represents the random variable, and y is some dummy variable which takes values between minus to plus infinity. And so now I take px of x and differentiate this, integrate this between minus infinity to y, right? It turns out that for this px, you cannot get a closed form expression for this, right? No closed form expression. Possible. Okay, we'll again come back to this. this is so important that the normal distribution comes in so many different areas that we need to evaluate this. So it's often evaluated numerically. I'll come back to its numerical evaluation shortly, right? And so this idea that I'm asking this question, what is the probability that x is random variable x is less than some value y, keeps occurring. So this is given a special name called the cumulative distribution function, or CDF, right? Remember, the D before stood for density function. That was the probability density function, and in this context, it is for distribution, right? So typically, um, it is given. It is represented as F as the CDF, and X is a random variable, and some value X. This means probability that random variable X is less than. Sorry. Okay, X. Okay, so this is the definition of CDF, and as we showed before, it is connected to the probability density function PDF. Okay, so I mean it's very easy to describe properties of CDF. First is CDF is a non-decreasing, right? Non-decreasing function of x. Meaning, if I have the real number line, if I have x1 and x2, then fx x1 will at least be less or equal to fx x2, right? That's because in defining x1, I would have covered certain events, and in defining x2, I would have covered every event that's already been counted in x1 plus something more, right? And so cumulatively, the probability gets added up. So we can make a statement that fx1 is always less or equal to fx2 as long as x1 is less or equal to x2, right? So that's the first property. So in that sense, it is a non-decreasing function of x, right? Closely aligned to this is the idea that if you start from the left extreme, that's minus infinity, this is 0, meaning you're now answering the question, what is the probability that random variable x is less than minus infinity? It cannot be, right? I mean, real number line has to start somewhere and has to end somewhere. That beginning and end, we have identified that as minus and plus infinity. So you can't ask the question, what is the probability that x is less than minus infinity? So that is a null set. So that probability is 0, right? Similarly, fx infinity is equal to 1, meaning if you go to the right extreme, that will include the entire sample space. So this is like asking, what is the probability that x is less than plus infinity? Okay, this includes the entire sample space. So that sample space has to be equal to 1. So this is probability that this is the entire sample space. So that's equal to 1. Okay, so the shape of the CDF is not known a priori for every problem. Suppose, right, in case fx of x is a continuous function of x, okay, then it's possible to differentiate the CDF and then get the PDF, right? So this is only a limited occurrence where the function CDF function is continuous, and I can differentiate this everywhere, right? if the CDF has impulses, sudden increase, and so on, where the left derivative and the right derivative will not be equal, right? So in which case the PDF cannot be defined, right? Or PDF will be a mix of some continuous smooth function and impulses, right? I mean, it's possible to build those things, but they don't make much sense, okay? Because that would mean that a random variable, a continuous random variable, takes a certain value, that is capital X will be equal to some x naught, right? And so only when I mix a continuous and discrete random variables, we will have situations where there are sudden jumps or impulses in the PDF description. Okay, so another idea is that of a complementary CDF, right? Okay, remember that in CDF I defined probability that random variable X is less than X, right? It's possible to ask the question, what is the probability that X is greater than X, right? This definitely is 1 minus probability that X is less than X, right? And so this has been called as the CDF fx of X. This is will be called as the complementary of this fx complementary of X, right? So sometimes a complementary becomes important, right? We'll quickly look at those situations where the complementary is important. Again, let's go back to the Gaussian. So let's say this is a value m and my Gaussian is symmetric, and I often ask the question, what is the probability that in this Gaussian PDF that is with mean m and variance sigma square, this value is greater than x naught, where let's say, for example, x naught is greater than m, right? I ask the question, what is the probability that random variable X is greater than X naught? That is, it is this probability, what is called as the tail probability. Meaning, it's the area under the curve of the Gaussian for values of X greater than X naught, right? And typically, because you saw that Gaussian is an exponential, it falls off very rapidly. So the tail probabilities are extremely small, right? We will calculate tail probabilities when we come to analyzing digital communication. They are typically of the order of 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 3, and so on, right? So these tail probabilities for the type of a Gaussian curve are they tend to be extremely small, right? And we of course don't know how to evaluate them, but nevertheless we can associate with this probability that X is greater than X naught. Okay, and that's the origin of this complementary CDF, right? There is in fact a complementary function that some mathematicians and communication people use, what is called the ERFC, right? ERFC stands for error function complementary, but we will not use the error function complementary. We'll use what is called the Q of X. Okay, let me just quickly define what is Q of X. Suppose I have a normalized Gaussian of mean 0 and variance 1. So that means the PDF the PDF function looks like this. The mean is 0, so there is no x minus m term, and the variance is 1, so sigma square is 1, so it is e raised to minus x square by 2. So if you sketch this, this will be symmetric about 0. This is my Px of x. And I ask the question, what is the probability that random variable x is greater than x naught, where x naught is greater than 0. Okay, so it is this tail probability, and by definition, this is x naught to infinity 1 by under root 2 pi e raised to minus x squared by 2 dx. And as I said before, no closed form expression is possible. It is not possible to integrate this. And so this is given, this is used as a definition of q of x naught, right? So q of x naught is the a tail probability, that is this probability of a Gaussian random variable whose first parameter called the mean is equal to 0, whose second parameter called the variance is equal to 1. And for that, if x naught is greater than 0, x naught lies on the right of 0, so only then I can define what is called q of x naught, and this whole thing is the definition of q of x naught, right? And it is so important in statistics, in communication, in so many different areas, in management, in financial markets, and so on. This q of x naught is computed for different value of x naught, positive values of x naught, pre-computed in the form of tables. It's also available in most C programs as a function. You can simply pass the argument and get the value q of x naught. It's available in many advanced packages like MATLAB, Scilab, and so on. So, or in Python. So, most numerical libraries incorporate this function. So, you simply pass on the argument x naught, assumed to be positive, and q of x naught, you can get back the value. Okay, and what is interesting here is I have a symmetric plot like this, and somewhere here is positive x naught. It's possible that I can, instead of asking what is greater than x naught, I can ask what is less than, what is the probability, that random variable x is less than minus x naught. That is this tail probability, right? So the question is, how do you calculate this? For x naught positive, right? If you ask the question for a Gaussian of parameter mean 0 and variance 1, if you ask the question, what is the probability that the random variable x is less than minus x naught, right? By the symmetry and so on, it's possible to show that this is equal to q of x naught only. So this area is equal to this area, right? And so even though I'm looking at minus x naught, I can now look at same value q of x naught defined before. Okay. Second a situation we often encounter is somewhere here is x naught and this is 0, 1. I want to know this probability, right? I want to know this probability. Not so this easily becomes 1 minus q of x naught, right? So this is q of x naught, this is q of x naught, right? And so if you want, let me hash put red hash here, right? And this becomes 1 minus 2 of q x naught, because the whole area under the curve is 1. I'm removing one q x naught from here, I'm removing another q x naught from here. So what is marked in red in this plot is one q x naught removed, another q x naught removed, so it becomes 1 minus 2 twice q x naught. So it's possible that once you have access to a function called q, right, yeah, you can answer many questions, right? You can also answer a question such as, let's say I have x1 here, I have x2 here. So I asked the question for Gaussian 0, 1, what is the probability that x lies, x is greater than x1 and less than x2? Maybe you can make it equal, it doesn't matter, right? By definition, this is minus in, sorry. And where both x1, x2 are positive, x1, x2, px of x dx. This can be seen as, you know, um, it's this probability. So you can take this as x1 to infinity px of x dx, and this probability you can subtract out x2 to infinity px of x dx. So by definition, this is qx1 minus 2qx2, right? So this indicates that even though x2 is greater than x1, right, the function of q, if you look at this tail probability, qx2 is less than qx1. So in a very counterintuitive way, right, the way when we defined CDF, we had the higher value. It would have been fx x2 minus fx x1, but q being the complementary of that, the arguments x1 and x2, they exchange their places. Okay, so there are many other PDF functions are possible. I can give you another more examples of what is called an exponential random variable. Okay, so x is an exponential random variable. This has a parameter p lambda. Okay, Gaussian had two parameters, m and sigma square, whereas exponential has only one parameter lambda, and its PDF px of x is lambda e raised to minus lambda x for x greater or equal to 0, and 0 for x less than 0. Okay, so this is a functional form, right? So if you want to sketch this, it looks something like this. This is the PDF of this, right? For x less than 0, it is 0. Okay, so it's only defined for positive values or non-negative values of so for this, it's possible to sketch the CDF, right? So a CDF is fx of x, that is integration from minus infinity to value x and lambda e raised to minus y dy. Okay, and this form is very easy to integrate, unlike the Gaussian where it was e raised to minus x square, which is not easy to integrate or which is not possible to integrate at all. This can be integrated, right? This can be integrated, and I want you to go home and show that this is e raised to minus lambda x, right? And so this can be sketched, right? Fx of x, right? If x is 0 or less than 0, it is all 0, and then if x is infinity, it goes to 1, right? And so it slowly increases and flattens off. As x takes higher and higher positive value, the probability increases, right? And so it's possible to draw a nice and smooth CDF function, right? Okay, so just like the continuous random variables have um, uh, expressions and parameters, even the discrete random variables, right, they also have expressions and various manifestations. So one very useful thing is what is called the binomial random variable. So where the random variable x, right, takes integer values 0, 1, 2, and so on up to value n, right? So this has two parameters. The first parameter is what is called the p, a value between 0 and 1, and n, right? I need to specify n, and x then takes values between 0 and n. Okay, so we ask the question, what is the probability that x takes value equal to some k, right? Often shown as px. Oh, sorry. Px of k, right? And by in the binomial definition, it is n choose k, right? And p to the power of k and 1 minus p to the power of n minus k. So where p and n are the two parameters which characterize the binomial random variable, right? And here x takes finite values. It can take value 0, an integer 1, 2, and so on. So it can only take integer values between 0 and n, right? And for every integer value in that range, the probability that it can take is given by this binomial expression, right? N choose k, and as before, n choose k is n factorial, n minus k factorial, and k factorial, right? And so you can find out what the value is. There are very many interesting approximations to this. You can show that if n is very large, this shape of this curve, even though it is discrete, it is a probability mass function, even though x takes only integer values, as n becomes large, right, you have more and more stems or the vertical lines. And if you stand uh, if you take a top view of this, that looks like a Gaussian, right? And so there's a very interesting approximations possible. There is a thing called Stirling's approximation for n factorial. So, and that comes into play, and that translates this, seemingly simple expression, right? Which you're probably aware of since your 11th and 12th class. This appears, or this approximately becomes, a Gaussian random variable, right? Not in the sense that one is discrete, other is continuous, but the lines appear more and more dense. So the density function, it collapses into a Gaussian, right? And that can be shown. And one of the inputs that we use for that is the factorial. There is a thing called Stirling's approximation. So those of you who have seen it before or want to go back and check, it's possible to simplify this as that. Okay. So now, having shown this, is there any question so far? Any question? Okay, so maybe one more PDF I'll introduce. Very interesting PDF that is very important in communication is what is called the Poisson random variable. Okay, where this has a parameter lambda, right? So this is characterized by parameter, just like the exponential parameter lambda, right? In fact, this lambda and the one in exponential are related. We will explore the relationship later on, or if you take some courses in computer networking and so on, you see a constant interplay between a Poisson and exponential, right? Where random variable x takes integer discrete values 0, 1, 2, and so on, unbounded, right? Whereas in the case of binomial, we stopped at n. In the case of Poisson, it's unbounded, right? And probability that x takes some value k, right? K is an integer, is given as lambda to the power of k e raised to minus lambda by k factorial, right? A very interesting situation here, and k takes value 0, 1, 2, and so on up to positive infinity, right? Uh, okay, and Poisson is a very useful model in communication where we want to model the incoming traffic. Um, you know, at any given point in time, how many people are trying to make phone calls, or how many people are trying to send emails, and so on. And it turns out that many such situations where many independent entities, right, are executing a similar function, such as making a phone call or sending an SMS or sending an email. So these are captured by a Poisson random variable kind of a model, right? So a very useful model. Later on, we will also describe simple operations on random variables called expectations, averages, and so on. So lambda turns out to be the average value of the expectation, right? So now that I have defined a single random variable, it's very easy to extend this idea to multiple random variables. Okay, where the same probability space, right, and I have a real number line. So a point omega maps to some value by function x1, right? So x1 is some kind of a mapping function. The same omega maps to some other value by a mapping function x2 and x3 and so on. So x1, x2, x3 and so on are different ways of mapping, okay, different ways of mapping the same sample function to the real number line. Okay, this may map to some value x1, this may map to some value x2, this may map to some value x3 and so on, right? So we often ask the question, what is the probability that x1 is less than this and x2 is less than this and x3 is less than this? So we ask this interesting cumulative question, right? I have x1, x2, x3. I ask the question, what is the probability that x1 is less than some value x1, at the same time x2 is less than some value x2, and x3 is less than some value x3, right? So this is the subject matter of multiple random variables, right? Whatever that we have seen before just extends to this, right? This means sorry, I think I should have, okay, let me change this. x1, x2, x3. This means the probability that x1 is less than or equal to x1, and that at the same time x2 is less than or equal to x2, and x3 is less than or equal to x3. Right? So I now have multiple events, right? And I'm asking this question at the same time, so everything gets ANDed. So it is at intersection. I'm interested in the intersection. I'm not asking what is the probability that x1, random variable x1, is less than x1. I'm saying at the same time x2 should be less than x2. At the same time x3 should be less than x3. Right? So this multi-dimensional function, let me sketch it for a simple illustration. So I have here x1 random variable, x2 random variable. Here is some value x1, here is some value x2, right? So this space indicates where random variable x1 is less than x1 and random variable x2 is less than x2, right? And so I'm looking at this region shaded by red as the region where this situation holds good. So by extension, I can now define joint PDF of probability x1, x2, and parameters x1, x2, right? Or dummy variables x1 and x2, right? So I can take this and integrate this so I can carry out integration, right? I've shown explicitly double integration, but where x1, x2, right, belong to the shaded region, right? So I carry out this integration, this double integration in the case of two random variables or more, right? So the situation can get more and more complicated if I bring in more and more applications, right? So I think I stop here now, and let's see if there are any questions. Let me know, or you would send me email with questions, and I would like to maybe then I would uh, you know try to answer them over email to everybody. Okay. So how many of you are still in the campus? Okay. Is there anybody who's connecting from outside the campus?
Yes, sir.
I'm
Okay.
connecting out.
Okay. So, are you connecting from mobile phone?
Hello. Fiber.
Laptop.
Oh, laptop. Okay, 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 okay. So, uh, is a video visible? Is the video, okay? Or are there a lot of breaks in the video?
Not in good quality.
And the audio is okay?
Yeah.
Qu- Quality of audio also is okay?
Yeah, audio is fine. Video has a little latency, but it's fine.
Okay, great, great, great. Okay, okay. So, it's good that I had so many people participate in this experiment. We are trying to understand how to do this in a much larger scale, so that in case the situation extends, we could do remote lecturing like this. Though as a teacher, I find it very strange that I don't have anybody sitting in front of me. I'm used to seeing faces. I mean, I don't get the same energy when I'm looking into the camera, right? Okay, but anyway, this is a new situation and a new experience. Okay, please wait for my further instructions. I stop for the day here. Okay, yeah, bye. So, how many people came? I think 30 people. 30 people came. Okay, okay. Saved. Oh, so I have to stop recording, no? Stop sharing. Just click here. Okay, I'll talk to my. How do I stop? Yes, people did. Um, what happened? It's unmute, sir. It's unmute. Okay, okay. So people did join from outside. I don't know how many joined from outside, but I can get that. Mahesh, I can try to find that. Data, but people did join from outside, right? So the video isn't visible now. The video quality looks all right. Anybody joining from outside? Okay, okay, fine. Thank you, Mahesh. How do I stop recording? Here. Stop recording. Okay.